Alright, let's just see where we are. We've been looking at the Earth system, which is the atmosphere, the thing that we're going to be most interested in, but also the biosphere, the hydrosphere, the cryosphere, and all the other spheres that we can think of, and we've been looking at some interactions between them. And we've also looked at some cycles, the water cycle and the carbon cycle. There is a little bit of a discussion about oxygen in the textbook. The main question about oxygen is, where did the oxygen come from? The earliest atmosphere had no oxygen. The current atmosphere has oxygen. Atomic oxygen, molecular oxygen, the stuff we breathe, and O3, ozone. It was not there originally, so it's of interest to ask, where did it come from? But I'm going to let you read that material for yourself. What we're going to move on to next is a quick overview of how our climate has changed. And to understand that, we're going to take a little bit of a look first at the topic of isotopes, because they have proved to be very interesting and useful at helping us figure out climate change. So we have a couple of questions about isotopes. First of all, what the heck is an isotope? If you're like me, you need to spend some time reminding yourself about what is an isotope. And secondly, why on earth would we even remotely care about isotopes? So let me spend a couple of minutes trying to explain what isotopes are and why we care about them. Here's our first question: what are isotopes? Alright, think of an element, any element, but for the purposes of studying climate, things like oxygen and carbon will come to mind. And from the periodic table of elements, we know the atomic structure of these elements. We know how many protons and neutrons, electrons they have. However, it turns out that under the right circumstances, you can get variations in these quantities. So here's an example. When we think of standard oxygen, it's written as O16, meaning that it has 8 protons and 8 neutrons in the nucleus. So far so good. That's basic oxygen. However, under the right circumstances, and we'll come and talk about those in a minute, you can also get O18 instead of O16, and this has 8 protons and 10 neutrons in the core. And so this gives us a little bit of an idea of what an isotope is. Isotopes are variations on a theme with a given substance, oxygen, carbon, whatever, where there are a different number of neutrons in the core of the atom. And these things are called isotopes, and they're written in this kind of notation here. Okay, so when you see this notation, you need to think, isotopes. Now, if you're like me, as I mentioned just now, and you've forgotten about isotopes, here's a YouTube video you can watch. I'll just get the thing rolling. Let's see if this works.
What are isotopes? Isotope is a word that gets thrown around in chemistry a lot.
Okay, so it's a guy telling you what are isotopes. But it's actually a pretty helpful discussion. So if you can't remember what isotopes are, watch the video. I've given you also another link here that explains oxygen isotopes. And for our purposes in the atmosphere, it turns out that different isotopes preferentially evaporate more easily and condense more easily. Who would have thunk it? And as a result of this link, which I'm going to show you here, we get to understand how isotopes help us unlock past climate. So this is a NASA link, and it looks like this. So this is a little bit of a discussion about a field of study called paleoclimatology, which is the study of ancient climates, and in particular how we can use oxygen isotopes to unwrap the mysteries of ancient climates. And we'll be talking about that a bit more in a minute. But there's some discussion here about isotopes, and here are a couple of little spinning cartoons of what the core of an oxygen atom might look like in either O16 or O18 form. And if you try hard enough, you'll count a couple of extra neutrons in this case. So there's some discussion here about what an isotope is, and then there's some discussion which is particularly interesting for us about why we care about isotopes. Here we go. Water molecules containing light oxygen, O16, evaporate slightly more readily than water molecules containing heavy oxygen, O18. Water molecules containing heavy oxygen, O18, condense more readily. So the two isotopes of oxygen, when you put them into the form of water vapor, H2O, there's your oxygen, will cause evaporation and condensation to behave slightly differently. Here's a tiny example of how that would make a difference. Suppose that we've got some liquid water here, and the H2O molecules inside contain some light oxygen, O16, and also some heavier oxygen, O18. So the evaporation process favors the lighter oxygen. So there's a tendency for the O16s to evaporate before the O18s. Okay? Now you can see that there are going to be a couple of results of this. Inside the water droplet, if all of the O16 is leaving, then there is an enrichment of O18. And then the opposite on the outside in the vapor. If the O16 is preferentially evaporating, the outside O16 is going to be enriched. And so that's one example of why we care about these isotopes. Alright, so you remember we had two questions. What is an isotope and why do we care about isotopes? So let's go back and finish off our list. I've given you enough clues to understand why isotopes could be very powerful in helping us unlock the mysteries of past climates. And I'm just going to give you a couple of examples out of the book here. This is about the oxygen isotopes. Let's see, where is this in the book? This is page 48. In cores of ocean sediments, oxygen 18 amounts are enhanced at times when surface ocean waters are cooler. Okay, so you can take cores of ocean sediments going back in time, and you can measure the ratio of O18 to O16 in the cores, and that gives you a record of ocean temperatures in the surface waters back over time. And by the way, where do you get the time axis from? You get that from carbon dating. In other words, you get a core of this muck at the bottom of the ocean and a thin slice of it. You look at the O18, O16 ratio. That tells you what the temperature was, and then independently carbon dating tells you how far ago this was happening, and therefore it tells you the time axis. And here's a second example involving now carbon. Low amounts of C13 in organic deposits indicate high levels of CO2 in the atmosphere at the time of plant growth. So we can examine the ratio of C13 to C12 just as we examined the oxygen ratio, and that gives us a record of CO2 concentrations back in time. Again, carbon dating tells us what the time axis was like. And so summarizing all of this then, isotopes and isotope ratios give us proxy data for past climates. What are proxy data? Well, let's just pick a random time 100,000 years ago. Nobody, as far as we know, was standing around 100,000 years ago taking temperature measurements with thermometers or any other kind of devices. And even if they were, There were no books or computers to record the measurements in, so we have no actual temperature measurements 100,000 years ago. But instead we can use proxy data to figure out how cold it was relative to now, or how warm it was relative to now, or wet or dry 100,000 years ago. And that's what proxy data is, and that's what isotope data gives us.